Hi! In today's lesson, we're going to be learning about isotopes, what they are, what they mean, and how we can use them to calculate average atomic mass. So let's go. Isotopes are atoms of the same element with different mass numbers. So let's break that down for just a moment. We know that every atom of an individual element, for example, gold, every atom of gold will have exactly the same number of protons, just like every atom of helium will have the exact same number of protons. Helium is atomic number 2. That means it has 2 protons, no matter what. So if the mass number is different in an atom that is an isotope, is it the protons or the neutrons that are changing? Well, we know we can never change the number of protons. So this has to be some change in the number of neutrons in that species. So for example, here's a symbol for our element carbon. Its mass number is 12 and its atomic number is 6. That means it has 6 protons, 6 electrons, and 6 neutrons. If we were to write this in what we call hyphen notation, we would write it as carbon-12. However, this isn't the only form of carbon. For example, here is another representation of carbon-12. If we look closely, you can see there are 6 positive protons and 6 neutral neutrons in this atom of carbon-12. 6 neutrons, 6 protons, 6 electrons. But let's compare it to this atom a little further down the page. How many protons do we have here? Well, we still have 6. But what about the neutrons? Well, in this example, we have carbon-14. We have 8 neutrons, 6 protons, and 6 electrons. Carbon-14 would be a radioactive isotope of carbon-12. Carbon-12 is the more common stable isotope. Carbon-14 would be a radioactive isotope. Most atoms have either a stable form and a radioactive form. Some elements that are high up on the periodic table, for example, everything above number 83, they actually have no stable isotopes. All their isotopes are considered to be unstable and radioactive. You might have remembered learning about carbon-14 when you discussed radiocarbon dating when you took earth science. It's an element that we can use to figure out how old remains are or once living things are. You could use this to date, say, a piece of wood turned up during an archaeological dig. But it wouldn't be any good for dating stones or rocks because those were never alive. So carbon-14 is a radioactive isotope. It has 2 more neutrons than our standard carbon-12. There are lots of different isotopes. Let's take a look at chlorine-37. Chlorine-37, what is its atomic number? Its atomic number would be 17. What is its mass number? Well, that would be 37. How many protons does it have? How many electrons does it have? Remember, our electrons and protons are always going to be the same number in a neutral atom. How many neutrons would chlorine-37 have? If you said 20, you are absolutely correct. Now, that's not the only. Chlorine-37 is an isotope of chlorine. Here are 3 isotopes of hydrogen. The first one is just hydrogen as we know it. It's just 1 proton, 1 electron, no neutrons at all. Our second one is deuterium. Deuterium is still just hydrogen, but it has a mass number of 2 because it has one proton and one neutron. Hydrogen doesn't normally have a neutron. Our third isotope is tritium. It's called tritium because it has a mass number of 3, and it has 2 neutrons in addition to the proton that's normally in hydrogen. Tritium's actually very radioactive. We used to use tritium in the lab to radioactively tag DNA before we used to do gel electrophoresis, if that's something that you remember back from when you took living environment or biology. So let's do some problems with some isotopes. I want you to determine the number of neutrons and protons in each of these 2 isotopes of uranium. So uranium is symbol U on the periodic table. Let's start with uranium-238. Uranium-238 would have 92 protons and 146 neutrons. That's a huge difference. Uranium-235, on the other hand, would also have 92 protons, but it would have 143 neutrons. Remember, our mass number is equal to the number of protons plus the number of neutrons, so we can subtract our proton number or atomic number from our mass number and always arrive at our number of neutrons. Now, I've asked you another question here. Which of these 2 would be more abundant? Now, what does that mean? Really, I'm asking which of these 2 would be more likely to be found in nature? Which one is its most common form? How can you find that out? Well, I'm going to give you a clue. Look at the atomic mass and compare it to the mass number of each. If you compare your mass numbers to the atomic mass, you want to ask yourself, which of these mass numbers is closer to the atomic mass given on the periodic table? Whichever one is closer, that is the most abundant isotope. So which one here is more abundant? In this case, our more abundant isotope would be the uranium-238. Let's try another example. In this problem, I'd like you to try to determine what is the mass number of calcium's most abundant isotope. So if this is calcium, and its atomic number is normally 20, and its atomic mass is 40.078, what would be the mass number of calcium's most abundant isotope? Well, in this case, the answer would be 40. It would be 40 because 40 is closer to 40.078 than 41 or 39. So 40 would be our most abundant isotopic form, calcium-40. Let's look at another example. Is a magnesium isotope with a mass number of 33 AMU common or abundant in nature? Explain. If you said no, this would not be abundant in nature, you are absolutely correct. If we look at the atomic mass of magnesium, it is 24.305. This is very far from 33 AMUs in our mass number of this imaginary isotope. A magnesium with a mass of 33 would be exceedingly rare. It would be highly unstable because it would have a very large number of neutrons. Let's try example 11. Which of these 4 symbols would be reasonable for a common isotope of carbon? You might be giving more than one answer here. In example 11, if you chose carbon-12 and carbon-13 as your reasonable isotopes, you would be absolutely correct. Carbon-6 would have no neutrons at all. That would be very far out of the norm. And carbon-18 would have 12 neutrons, which is 6 more than normal. When we get too far away from the common isotopic mass, we become less and less likely to exist. So carbon 6 and carbon 18 would be very unlikely. Thus your answer would be carbon 12 and carbon 13.